Welcome to the cosmos of discovery, where the boundaries of our understanding are constantly being pushed by new and incredible findings. The James Webb Space Telescope is currently engaged in the remarkable task of identifying celestial objects from the Dark Ages, an era for which our best measurements indicate the presence of large, fully developed galaxies. This mission was commissioned by NASA, which allocated a budget of $10 billion for the project. Although the James Webb Space Telescope has been in space for just over 2 years, the breathtaking results it has already provided are undeniably worth every penny. Historically, our most spectacular views of the cosmos came from previous telescopes, but as of July 2022, the James Webb Space Telescope has transcended all that we have previously witnessed. It has taken us to new frontiers, offering glimpses of the faintest galaxies, the richest clusters, vast cosmic voids, and the farthest reaches of space, among countless other discoveries. This superior telescope has unveiled unprecedented details, exceeding all expectations. One of its most astonishing revelations occurred when the James Webb Space Telescope focused on regions of space that appeared void to the Hubble telescope. To our astonishment, it detected a mind-boggling disappearance of 900 trillion stars into the vast expanse of space. This perplexing phenomenon raises numerous questions. What could have caused this mass disappearance? Where did these stars vanish to? How did they seemingly vanish without leaving a trace? Join us as we delve deeper into the shocking discovery made by the James Webb Space Telescope and unravel the mystery of the disappearing stars. The potential impact on our planet and our future is a crucial consideration. To begin, it's essential to understand that the James Webb Space Telescope has exceeded our expectations in its performance compared to the Hubble telescope. When you compare the capabilities of the James Webb and Hubble telescopes side by side, the differences are remarkable. The primary mirror of the Hubble telescope measures 2.4 meters in diameter, while James Webb's segmented mirror spans an impressive 6.5 meters. This significant difference in mirror size translates to a resolution that is 270% sharper for the same wavelength of light and a light-gathering power that is a staggering 730% greater than that of the Hubble telescope, solely due to the physics of optics. This means that James Webb should inherently outperform Hubble, both in terms of quality and speed. It's important to note that these advantages do not even take into account the additional benefits that James Webb possesses in terms of cooling, wavelength coverage, and advanced instrumentation. In other words, for the same amount of observing time, you would expect James Webb to collect 730% more light than Hubble. As seen in the comparison of their composite images, such as the one showing galaxy cluster SMAC E723, James Webb is performing even better than these impressive expectations. Hubble's observing time is divided into orbits, as it completes a revolution around our planet every 96 minutes from its position in low Earth orbit. This exceptional performance by James Webb opens up exciting possibilities for scientific exploration and discovery. In total, 6 orbits were dedicated to capturing the Hubble composite images, 4 in optical wavelengths and 2 in infrared wavelengths. At first glance, straightforward math might suggest that 6 orbits, each lasting 96 minutes, would accumulate to 9.6 hours, equivalent to 576 minutes of Hubble observation time. However, the reality is that only a total of 3.4 hours, or 203 minutes, of Hubble data contributed to these images. This is despite the fact that nearly 3 times as much of Hubble's time was allocated to this particular target. To put this in perspective, let's compare it to the James Webb Space Telescope's approach. James Webb observed the same target for an uninterrupted 12.5 hours, and it consequently obtained a full 12.5 hours worth of data. The key difference here lies in their respective locations. Hubble, being in orbit around Earth, spends over 50% of its time with the Earth and its atmosphere obstructing its view of the desired target. Useful data can only be gathered when the target is in a completely unobstructed line of sight with the telescope. On the other hand, James Webb is positioned approximately 1.5 million kilometers away at the L2 Lagrange point. It continuously faces away from the Sun, Earth, and the Moon, eliminating any obstructions. It never contends with these obstacles, ensuring pristine, observing conditions. Consequently, James Webb's observations of targets are 100% time efficient, in stark contrast to Hubble's efficiency of less than 50%. This enhanced efficiency extends to all observations conducted with the James Webb Space Telescope. The James Webb Space Telescope promises to deliver faster and more advanced scientific insights than the Hubble telescope ever could. In other words, James Webb has provided compelling evidence that goes beyond mere theory. Not only can James Webb locate celestial objects that were previously invisible to Hubble, but it can often resolve these objects and scrutinize their characteristics in intricate detail, something Hubble was incapable of achieving. This capability aligns with one of James Webb's primary scientific objectives, to provide us with the most precise and comprehensive understanding possible of how our universe evolved and reached its present state. For instance, James Webb has provided unprecedented views of nearby Jupiter, revealing its bands, rings, moons, and even placing them alongside distant background galaxies. Additionally, the telescope has directly observed exoplanets using infrared imaging and spectroscopy, allowing us to detect absorbed and transmitted light, uncovering the presence of various molecules. Star-forming nebulae have been observed in remarkable detail, showcasing everything from newly formed blue stars to intricate gaseous features. James Webb has achieved what Hubble could not. Furthermore, the initial alignment image of James Webb has grown into a spectacular 140-plus megapixel view, revealing far-flung galaxies in abundance. Even just 1% of this view contains 1 to 100 identifiable objects, including massive, evolved, and complex galactic structures at various distances. The wealth of information and the quality of the observations made by James Webb are truly extraordinary, marking a significant leap forward in our exploration of the cosmos. Surprisingly, James Webb has unveiled potential cosmic candidates that emerged at extraordinarily early stages of the universe. Additionally, it achieved the remarkable feat of capturing imagery of the most distant star ever recorded, known as Arundel. However, perhaps the most extraordinary images produced by James Webb are those of individual galaxies. Through its lens, we gain unprecedented insights into these galaxies, with views revealing intricate details such as gas, dust, stars, and the central black hole containing cores. These cores shine brilliantly in mid-infrared light, while star-forming gas bridges become apparent in the spaces between interacting galaxies. When we compare the observations made by Hubble to those of James Webb, and from near-infrared to the eerie yet captivating mid-infrared views, it becomes evident that the universe is coming into sharper focus than ever before under James Webb's vigilant gaze. However, amidst these remarkable discoveries, a shocking revelation has surfaced. James Webb has detected the inexplicable disappearance of trillions of stars without a trace. The burning question arises, how and where did they vanish? Two leading theories have emerged to explain this baffling phenomenon. One suggests that these stars may still exist, but are in a state of diminished luminosity, perhaps obscured by dust, or are undergoing a gradual decline without the dramatic spectacle of a supernova. The other theory posits a more startling possibility. These stars may have abruptly collapsed into black holes, skipping the supernova phase altogether. In the bleakest scenario, it raises the unsettling possibility that the universe itself might be undergoing a gradual disappearance, and our capacity to intervene or prevent it is beyond our reach. Nearly a century has passed since scientists first proposed the idea of the universe's expansion, wherein galaxies appear to recede faster as they move farther away from us. It's important to note that this apparent recession is not due to the physical motion of galaxies. The apparent motion of galaxies moving away from us is not due to their physical movement, but rather stems from the gravitational forces acting on objects in the universe and the expansion of the space in which these objects exist. This perspective has been the prevailing view since the 1920s. However, this long-held view has undergone significant revision in recent times. Approximately 2 decades ago, we made a groundbreaking discovery. The expansion of the universe is not only ongoing, but is actually accelerating over time. As a result of this acceleration, individual galaxies will progressively appear to move away from us at an increasingly rapid pace. Eventually, they will reach a point where they become completely unreachable, even if we were to attempt to approach them at the speed of light. Consider this: when you gaze at a star whose light has traveled toward you for 100 years, you are observing a star that is located 100 light years away from us. This is due to the finite speed of light. However, when you observe a galaxy whose light has journeyed toward you for a staggering 100 million years, it doesn't mean that the galaxy is precisely 100 million light years distant. In reality, it is considerably farther away than that. This occurs because, on cosmic scales, objects that lack gravitational binding into galaxies, groups or clusters, are subject to the expansive nature of the universe. In essence, the longer it takes for a photon to traverse the vast expanse from a distant galaxy to our observation point, the more the universe's expansion causes that galaxy to appear even more distant than one might initially assume, based solely on the time it took for the light to reach us. The extent of the universe's expansion plays a significant role in what we perceive through our observations. This implies that the galaxies situated at the farthest reaches of the cosmos are even more distant than the mere amount of time it took for their light to travel to us would suggest. This phenomenon manifests as a cosmic redshift. To elaborate, light is emitted with a specific energy and, consequently, a specific wavelength. We would naturally anticipate that this wavelength would remain constant when it reaches its destination. However, when the fabric of the universe is in a state of expansion, as depicted in the accompanying video, the very space through which the light travels is stretching. This stretching results in an elongation of the wavelength of that light, leading to the observed redshift. The pronounced redshifts we have observed in the case of the most distant galaxies have unequivocally confirmed this concept. Yet, we can glean more from this phenomenon than just the fact that the universe is expanding and continuing to do so. We can harness the wealth of information we gather to deduce how the universe has expanded throughout its history. This, in turn, provides insights into the composition of the universe. Once light departs from a distant cosmic source, the ongoing expansion of the universe causes the wavelength of that light to stretch, manifesting as a redshift. This effect becomes more pronounced for objects located at greater distances, leading to a clearer understanding of the universe's evolution and composition through careful analysis of these redshifts. The redshift of light becomes increasingly pronounced over longer periods of time, reflecting the changing dominance of various components within the universe. By conducting measurements on celestial sources at a wide range of distances, analyzing their redshift, and then comparing their intrinsic properties with their apparent size or brightness, we can reconstruct the entire history of the universe's expansion. Moreover, because the way in which the universe expands is influenced by the different types of matter and energy present within it, we can discern the precise composition of our universe. This composition comprises 68% dark energy, which is akin to a cosmological constant, 27% dark matter, 4.9% ordinary matter consisting of protons, neutrons, and electrons, 0.1% neutrinos and antineutrinos, and roughly 0.8% photons. Notably, there are no other components present, including no curvature, no cosmic strings, no domain walls, and no cosmic textures. With this comprehensive understanding of the universe's components, we can straightforwardly apply this knowledge to Einstein's general theory of relativity and predict the future destiny of our universe. When we initially applied this framework to the revelation of a universe dominated by dark energy, the implications were startling. Firstly, it implied that galaxies not already gravitationally bound to us would eventually vanish from our observable universe. Over time, galaxies would increasingly accelerate away from us as the universe continued its unchecked expansion, unaffected by gravitational or any other forces. As this cosmic expansion proceeded, the gap between a given galaxy and ourselves would continuously widen. This phenomenon results in the apparent motion of galaxies receding from us at ever greater velocities, driven by the expansion of the fabric of space itself. However, this leads to a disconcerting and inevitable conclusion. There exists a critical distance from our location. At this specific distance, due to the relentless expansion of space, a photon traveling either from our galaxy toward a distant one or vice versa, approaching ours from a remote galaxy, would never reach us. The expansion rate of the universe is so rapid that distant galaxies become entirely unreachable by our galaxy, even if we were able to travel at the speed of light. Currently, this distance stands at approximately 18 billion light-years away, and it's worth noting that the matter and radiation density continue to decrease while the overall expansion rate decreases as well. Considering that our observable universe has a radius of around 46 billion light-years, and that all regions of space contain roughly the same number of galaxies, this implies that only about 6% of the total number of galaxies in the universe are observable to us. Currently, the vast majority of the galaxies in our universe remain beyond our reach, even if we were to embark on a journey at the speed of light. This sobering fact underscores the reality that, on average, between 20 and 60,000 stars transition from being reachable to being unreachable every second. The light emitted by these stars a second ago may eventually reach us, but the light they emit in the very moment we observe them will never make it to us. It's indeed a disquieting and contemplative realization. However, there's a more optimistic perspective we can adopt. This is the universe's way of reminding us of the preciousness of every passing second. It's the universe conveying the message that if we aspire to venture beyond our local group, which consists of gravitationally bound objects like Andromeda, the Milky Way, and around 60 small satellite galaxies, we must act promptly. Each delay represents a missed opportunity. Of the estimated 2 trillion galaxies that populate our universe today, only approximately 6% of them remain within our reach from the perspective of the Milky Way. This fraction is gradually diminishing due to the accelerated expansion of the universe, driven by the influence of dark energy. This also implies that a staggering 94% of the galaxies in our observable universe are already beyond the grasp of humanity, emphasizing the urgency of our exploration efforts. The inexorable march of time brings every galaxy beyond our local group towards the same fate. Unless we develop the capability for intergalactic travel and venture into other galaxy groups and clusters, humanity will remain confined within our local group. As time unfolds, our ability to transmit or receive signals from the vast cosmic ocean beyond will progressively diminish. The relentless expansion of the universe persists, and the gravitational forces at our disposal lack the strength to counteract it. The universe's gradual disappearance is an unavoidable reality, and our powerlessness to prevent it becomes evident at this juncture. One of the most profound existential questions we can contemplate is how it will all ultimately conclude. By observing the universe today, deciphering its underlying laws, and witnessing the apparent recession of objects within it, we have discerned not only that the universe is expanding, but that this expansion is accelerating over time. Distant objects beyond our local group recede from us at ever-increasing velocities, heralding the eventual emergence of a cold, lifeless, and desolate universe, driven by the pervasive influence of dark energy. Many of us assume, in line with observations, that dark energy is a constant entity, with its energy density remaining uniform throughout the cosmos. However, if dark energy's influence grows stronger with time, it could dramatically alter our cosmic destiny, paving the way for a scenario known as the Big Rip. To comprehend the concept of the Big Rip, we must first delve into the motivation behind its consideration, which stems from the evidence supporting the existence of dark energy. To visualize the universe in its early stages, during the fiery birth of the hot Big Bang, we encounter a dynamic interplay of two contrasting forces. On one hand, there is the initial expansion rate, compelling everything to move apart at an accelerated pace. On the other hand, gravitational effects stemming from all the matter and energy in the universe work to counteract this expansive force, endeavoring to pull everything back together and potentially initiate a cosmic recollapse. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.